So now we have an intuition of best and how we want to split. We've looked over Michael's proposed sort of high-level algorithm for how we would build a decision tree, and I think we have enough information now that we can actually do a real specific algorithm. So let's write that down. And the particular algorithm that Michael proposed is a kind of generic version of something that's called ID3. So let me write down what that algorithm is and we can talk about it. Okay, so here's the ID3 algorithm. You're simply going to keep looping forever until you've solved the problem. At each step, you're going to pick the best attribute, and we're going to define what we mean by best, or a couple of different ways we might define best in a moment. And then given the best attribute that splits the data the way that we want, it does all those things that we've talked about, assign that as a decision attribute for node. Then for each value that the attribute A can take on, create a descendant of node, sort the training examples to those leaves based upon exactly what values they take on. And if you've perfectly classified your training set, then you stop. Otherwise, you iterate over each of those leaves, picking the best attribute in turn for the training examples that were sorted into that leaf, and you keep doing that, building up the tree until you're done. So that's the ID3 algorithm, and the key bit that we have to expand upon in this case is exactly what it means to have a best attribute. All right, so what exactly is it that we mean by best attribute? So there are lots of possibilities that you could come up with. The one that is most common, and the one that I want you to think about the most, is what's called information gain. So information gain is simply a mathematical way to capture the amount of information that one gains by picking a particular attribute, funnily enough. But what it really talks about is the reduction in randomness over the labels that you have with a set of data based upon knowing the value of a particular attribute. So the formula is simply this. The information gain over S and A, where S is the collection of training examples that you're looking at, and A is a particular attribute. It's simply defined as the entropy, with respect to the labels, of the set of training examples you have S, minus sort of the expected or average entropy that you would have over each set of examples that you have with a particular value. Does that make sense to you, Michael?
So what we're doing, we're picking an attribute, and that attribute could have a bunch of different values, like true or false, or short, medium, tall.
Right, and that's represented by V.
Okay, each of those is a different V, and then we're saying, okay, for over those leaves, we're going to do this entropy thing again, and right. So what is entropy?
Entropy. So we'll talk about entropy later on in the class in some detail and define it exactly and mathematically. And some of you probably already know what entropy is, but for those of you who don't, it's exactly a measure of randomness. So if I have a coin, let's say a two-headed coin that could be heads or tails, and I don't know anything about the coin except that it's probably fair, if I were to flip the coin, what's the probability that it would end up heads versus tail?
A half.
It's a half, exactly. If it's a fair coin, it's a half. Which means that I have no basis going into flipping the coin to guess either way whether it's heads or it's tails. And so that has a lot of entropy. In fact, it has exactly what's called 1 bit of entropy. On the other hand, let's imagine that I have a coin that has heads on both sides. Then before I even flip the coin, I already know what the outcome is going to be. It's going to come up heads. And so what's the probability of me coming up with heads? It's
1.
1. So that actually has no information, no randomness, no entropy whatsoever, and has 0 bits of entropy. So when I look at the set of examples that I have and the set of labels I have, I can count the number that are coming up, let's say, red X's versus the ones that are coming up green O's. And if those are evenly split, then the entropy of them is maximal. Because if I were to close my eyes and reach for an instance, I have no way of knowing beforehand whether I'm more likely to get an X or I'm more likely to get an O. On the other hand, if I have all the X's in together, then I already know before I even reach in that I'm going to end up with an X. So as I have more of one label than the other, the amount of entropy goes down. That is, I have more information going in. Does that make sense, Michael?
I think so. So is there, maybe we can say what the formula is for this, or
Sure. What is the formula for it? You should remember.
It's, if we have, well, I'm not sure what the notation ought to be with these S's, but it has something to do with log p log, wait, no, sorry, p log p.
So the actual formula for entropy, using the same notation that we're using for information gain, is simply the sum over all the possible values you might see of the probability of you seeing that value times the log of the probability of you seeing that value times -1. And I don't want to get into the details here. We're going to go into a lot more details about this later when we get further on in the class with randomized optimization, where entropy is going to matter a lot. But for now, I want you to have the intuition that this is a measure of information. This is the measure of randomness in some variable that you haven't seen. It's the likelihood of you already knowing what you're going to get if you close your eyes and pick one of the training examples versus you not knowing what you're going to get if you close your eyes and you picked one of the training examples. Okay?
All right. So, well, okay. So then in the practice trees that you had given us before, it was the case that we wanted to prefer splits that I guess made things less random, right? So if things were all mixed together, the reds and the greens, after the split, if it was all reds on one side and all greens on the other, then each of those two sides would have they'd have low entropy, even though when we started out before the split, we had high entropy.
Right, that's exactly right. So if you remember the three examples we had before, one of them, it was the case that all of the samples went down the left side of the tree. So the amount of entropy that we had didn't change at all. So there was no gain in using that attribute. In another case, we split the data in half, but in each case, we had half of the X's and half of the O's together on both sides of the split, which means that the total amount of entropy actually didn't change at all, even though we split the data. And in the final case, the best one, we still split the data in half, but since all of the X's ended up on one side and all of the O's ended up on the other side, we had no entropy or no randomness left whatsoever, and that gave us the maximum amount of information gain.
So is that how we're choosing the best attribute, the one with the maximum gain?
Exactly. So the goal is to maximize over the entropy gain. And that's the best attribute.